Yes, sir.
Okay, so we're going to continue from chapter 7 on in the handout. Let's pray as we start. Father, we thank you this afternoon. Thank you for another opportunity you've given us to be together. As we go through this class, we pray that you guide us through. In Jesus' name I pray, amen. All right, so we are looking at modes of failure, factor of safety, and some design equations, okay? So there are different modes by which a material or a machine element can fail. But we know that the primary purpose of a machine element is to resist the applied load on it. So in design, what we do is to ensure that we have the appropriate sizing of the various machine elements, and then based on the material that the element is made of, when that element or machine element is used, it will not be able to fail. Any load that is applied on it is able to withstand those loads. All right. And this is the part that must function, this part must function satisfactorily throughout its expected service life. So every machine element have a service life, because we know that when it's in operation, no matter what, a time will come that it will break down. But we ensure that within the period where the machine element is supposed to function, it should function appropriately without failing prematurely, okay? And when a machine part is no longer able to perform its function satisfactorily, it is considered as failed. For a chosen material, failure may be due to one, yielding. All right, failure may be due to yielding, and the yielding is a material property. All right, this is the material property used here is the yield stress. It is the point where we say that the material is going to yield. It's going to give in to the applied load. If the yield point is not well defined, as in the case of many ductile material, including aluminum and some alloy steel, we use the proof stress, which is either 0.1% or 0.2%, and it is the stress that will enable one to stretch a member from the original value by 0.001 or 0.002. Okay, so the material that yields, if it yields, we say that it has failed. And when the machine element is designed, we should ensure that to be able to operate at a stress value below the yielding stress of the material. Ultimate breakage. The material property used here is the ultimate stress, and it's important for brittle materials. Okay. For ductile material, we know that yielding will occur. Material will begin to elongate when we have tensile stresses on it. And by the point where it starts to elongate, it has not it's not yet broken, okay? But it will reach a point where it will just break. And that point is where we have the point where we can use the ultimate stress to define that point. And for brittle materials will not show any sign of yielding before it just breaks off. So when tensile loads are applied on it within a specific period of time, when the stress inside build up is more than that ultimate stress in the material, you will see that the material can just break off or fail. Then we also have fatigue failure. The material property is the fatigue strength amplitude, which is important for parts under variable stress conditions. So variable stress conditions here are when we have, let's say, cyclic loading in the member. And in such a situation, you see that the load is applied on the member and it's released. It's applied and it's released. Or we can have load that is reversed, okay, continuously, but it's reversed in amplitude. All right, so what happens is that it's going to subject the material to fatigue, and that may cause the material to fail or to break off due to that fatigue. Then we have unacceptable deflections. Deflections may also occur in the member, but we may not want deflection to occur because that may change the operation of the machine. Okay, for instance, if we take the crank, the connecting rod in an automobile or in an engine, nice engine, so the connecting rod which connects the crankshaft to the piston is straight, and we want to ensure that it is straight throughout the operation of the engine. And a situation where this connecting rod may break or it may deflect, right, where we have some bending occurring in the member, it may cause the engine to malfunction. It may jam up the engine, or the engine may end up being destroyed altogether. So in some situations, we don't want that deflection to occur. They are not desirable, so they are unacceptable. So when deflection occurs in such cases, then we can say that the material have failed or that machine element has failed. And the deflection may be due to axial loading or bending loading. So the axial loading is when the loading on the member is subjecting the member into compression. Okay, that may cause buckling to occur. Okay, so that leads us to the next one, which is the crushing or buckling. And this is important for columns and struts and other members in compression. So when we have members in compression, buckling or crushing may occur. And I gave an example of the testing the crushing strength of a rock, for instance. You may go to the geology lab to see how it's done. And when we are compressing it, you see that because the rock material is brittle, very brittle, it will crash. You will not see it bending or buckling. It will just crash. That is the failure of that rock material. When the crushing force exerted on it introduces some compressive stresses that are more than what the rock will handle, it simply crashes, and that causes it to fail. Then we also have buckling, and the buckling is where we see the material bending or deflecting. Okay, so you have let's say it's a ductile material, and it's not, let's say it's a slender member too, and we apply the load from above, it will subject that member to buckling. So it will somehow deflect or bend somehow. So that is also another form of failure. And then we also have unacceptable surface pressure. Unacceptable surface pressure. Okay. Surface pressure which occur on the surface of the material may also cause it to fail. Then we have other failure methods like the creep, wear, corrosion, and other things. Any question? Failure may not mean actual breaking of the material. Some machine parts are said to fail when they have plastic deformation set in them, and they no longer perform, they could no more perform their function satisfactorily. When that happens, we say that that material or that machine element has failed. But it doesn't mean that when we say something has failed, it means that it is broken completely. No. So we have different forms which I've explained that could that machine element has failed. Any question? Okay, let's continue. We are going to look at another important item in design, which is the factor of safety, and then what we call the design stress. Design stress, which is denoted by sigma D, is also known as the working stress or the stress. And it is stress induced to enable us have some safety margin. Okay, so when we have looked at all the different types of failure that may occur in the material, when the material is being designed or the part is being designed, we want to ensure that we have some safe margin such that within that margin, the material or the part can operate satisfactorily without any problem. And all the materials that we have, they have what we call the yield stress in the material, and then we have the ultimate stress in the material. And then the ultimate stress in the material, when the stress in the material exceeds that point, we see that breaking may occur. All right, so if you look at the stress strain diagram as we have here, this diagram, this tells us that from this point, okay, this line here, you see that the stress is directly proportional to the strain within this section here, okay? So the yield stress is sigma y, which is the yield stress in the material. Then from that point, we have the yielding occurring from that point. But as we are designing, we want to ensure that the stress, the maximum stress that, or the maximum amount of stress that the material will be subjected to will not be up to the yield stress. Because when we reach the yield stress, that means that failure is going to occur or is likely to occur at that point. So we need to leave some safe margin, okay? So that within that margin that we've left, assuming maybe due to certain conditions, the stress exceeds this design stress, we are still safe. We've not still reached the yield point in the material. Okay, so this stress, sigma D, is what we call the design stress, which we can also say that it is called working stress or the allowable stress. They are the same thing. So this is showing the stress strain diagram for ductile material. All right, so we have the yield point well defined. Now, well, let's look at this. So here, this is our the stress at which the material will fail. And then we put the design stress to be lower than the stress at which the material will fail. So this is the design stress. So it means that this stress is the limiting stress that when we are designing, we ensure that our design will operate within this limit, okay? And this margin between the design stress and this failing stress will be the safe margin for us. So we are the limit of the stress which must not be exceeded in the highly stressed cross-section of the member. So when we have the member, all right, when we have the member, the highly stressed cross-section of the member should not exceed the design stress. Let me go back and refer to something. When we're looking at this one, okay, you will see that you agree with me that we stretch this member, with this force, 12 kilonewtons from both sides. It will subject this to tension. And if we are to determine the stress along this section of this member, this shaft, you will see that the stress here will be less. It will be small, because we know that stress is equal to the applied load divided by the cross-sectional area. So the larger the cross-sectional area, the smaller the stress. But at this area here, where we have a larger the smaller cross-sectional area, with the same loading, the stress here is going to be greater, because this time the cross-sectional area is going to be small. And that means that if this member is to fail, it's likely for it to fail at the area where we have high amount of stress than at the area where we have less amount of stress. So that design stress, when we are looking at the design stress, we ensure that the highest amount of stress along the cross sections of the member, okay, should not exceed the design stress that we decide for the member. Okay, and if we are able to achieve that, then we can say that the member can operate safely without failing prematurely. All right, the design stress or the working stress is the stress assumed to occur in highly stressed part of the machine member. The design stress depends on certain things, and let's look at them. The properties of the material, okay, whether the material is brittle or ductile. So the design stress depends on the properties of the material, and also the service conditions under which the member is subjected to. Okay, so it depends on how the member is going to operate. So as we let's say you're operating a member 24 hours a day. Please mute your microphone. So if you're operating a member 24 hours a day, you need to be able to design the member to be able to withstand, because as you're operating it continuously for that long time, the fatigue stress it developed will be more, and many other things may occur during the operation of the member. Okay, so you need to ensure that it is taken into account the service conditions of the member. Then we also have the uncertainty of the loading conditions. So to depend on uncertainty of the loading condition, there are certain, there may be certain situations where you could not truly determine the condition of loading in the member. Many things may occur, okay? Let's take, for instance, an airplane that is moving through the air. Right, as it's going, depending on the weather conditions, the stresses built that may be built in the members of the plane will vary. And you cannot truly determine that, oh, at this point, this is how the stress distribution is going to be like, or at this point, this will be the amount of loading that will be acting on the plane. You can't determine that, okay? Let's assume that you are driving on the highway. And as you are going, many things may happen on the way that may change the stress distribution in the various members in the vehicle. So as you are going, for instance, apart from maybe the wind resistance that will be on the car, depends also on the road. Maybe you are going and you are not that careful. Before you know it, this is a speed ramp in front of you and you bump into it. And when you bump into that speed ramp, you see that it's going to induce more stress into the members of the vehicle. Right, so there are conditions that you could not truly determine how you could not predict. It may be that you cannot predict, or you cannot determine, or you may not be certain about, and therefore, as you are choosing your design stress, you need to know what the loading will be like on the member, and then how you should decide on the design stress. Okay. Okay, so the sigma F is the maximum stress the material can withstand without failure, or we call it the failure stress. Okay, so that is the maximum. Any stress that exceeds that failure stress, the material will fail. But in order to avoid plastic strain occurring in our member, we choose to work with the yield stress in ductile material as the failure stress rather than the ultimate stress. So because we don't want the material to yield, let's go to the stress strain diagram again. We don't want the material to yield, because yielding of the material in some situations means that the material has failed, though it's not yet broken, but it has failed. In order to avoid that, we use the yield stress in the material as the ultimate stress, or that is the maximum stress in the material. So that's our cutoff point. I want to ensure that we operate below that yield stress in the material. And that we call that yield stress. We can say that the yield stress is now functioning as the failure stress in the material. Then we also have the factor of safety. Okay, a factor of safety is used to keep the stress lower than the maximum or ultimate stress at which the failure of the material takes place. Because if you reach the maximum stress, let's say the yield stress or the ultimate stress where the material is failing, we don't want to get there. There may be a certain situation that will subject the material to a higher stress such that the stress may reach the ultimate stress value or exceed it. And we don't want that to happen. And because of that, we need to bring in that safe margin so that the material would be able to operate with below the ultimate stress. Okay. And it is a factor used to provide a design margin over the theoretical design capacity to allow for uncertainty in the design process. So those uncertainties, you allow for them, okay? And you make room for those uncertainties. So in cases where the stresses built up in the material may be higher than your design stress, you are safe. But because of that safe margin you've put in there, those stresses may not reach the ultimate stress of the material, which may cause the parts to fail. Okay, the uncertainty could be any one of the number of, it could be any one of the number of components of the design process, including the calculations, the material strength, the manufactured quality, or the loads that are on it, okay, and etc. Maybe during the calculation process, you've made certain errors there which may affect your final results, okay, which may cause you to under design your part. If you create for safe, if you allow that safe room or safe margin, that may assist you or help you in that area. And then also the material strengths, okay? That you may say that, oh, this material is having this strength or that strength, but in determining the strength, maybe there were certain things that were not able to be done very well. The safe margin will save you. Okay, and then also manufactured quality. That during manufacturing, there are certain things that may happen. And I mentioned earlier that there may be what called the residual stresses that may be built up within the component, the surface finish of the material, and or the part, and many other things may affect the strength of the part. So if a safe margin is not allowed or is not considered, it may make that part to fail in cases where it's subjected to high amount of loads. And of course, the loads too. You may not predict correctly the loading conditions. Like the examples I gave, the loading conditions on the road when you are driving your vehicle will be depend on several factors on the road, okay, which you may not be able to predict or know. So at times it comes to you when you are not really prepared for it. And the vehicle you are driving should be able to handle it without failing. So in that case, you make room for that. So in cases where high loads, the material is subject to high load, it will still be able to survive. Then the factor of safety may be defined as the strength of the component divided by the load of the component. Okay, the strength of the component over load of the component. Strength could be the strength could be minimum, mean, yield, tensile, fatigue, and shear. Okay, and stress must the stress must correspond in type and unit to the strength. So the stress buildup should be corresponded or should correspond to the strength. Both the stress and strength must apply to the same point or set of points on the member being designed. Okay, so the stress and the strength must be applied to the same point or different set of points for the member that is being designed. Related to the stress, the factor of safety can be defined in general as the ratio of maximum stress in the member, right? The ratio of maximum stress in the ratio of maximum stress in the member to the working stress in the member. Mathematically, we can say that the factor of safety is the maximum stress in the member divided by the working stress. But the working stress here is the stress that we decide that the member should operate at this stress. The maximum stress is actually the stress that will be in the member. And if you find this to be able to determine what the factor of safety is. So the working stress is the one which the designer himself will have to decide or choose. Okay. In the case of ductile material, a yield point is clearly defined. In such a case, factor of safety is based on the yield point stress. And we can say that in ductile material, the factor of safety is the yield point stress divided by the working stress or the design stress. And for brittle material, the yield point is not defined. So what we know in brittle material is the ultimate stress, okay? That is the point where the material fails. And therefore, factor of safety is the ultimate stress divided by the working stress or the design stress. So these are various formulas for the factor of safety, okay? Depending on the what condition we are looking at, what type of material we are looking at. The selection of a proper factor of safety to be used in designing any machine component depends upon a number of conditions such as the material, the mode of manufacture, type of stress, general service condition, and shape of the part, okay? Therefore, the values of factor of safety are related to the lack of confidence in the design process. They are related to the lack of confidence in the design process. The lack of confidence or uncertainty arises due to various factors. For example, we have composition of material and the effect of variation on properties. Variations in material properties from place to place within a bar of stock, effect of processing, the local, and all these other ones are there, okay? And they are all the uncertainties which we need to look at to decide on the factor of safety. Each of the above factors must be carefully considered and evaluated. High factor of safety may result in unnecessary risk of failure. Although the magnitude of the factor of safety is at the discretion of the designer, there are guidelines for each choice, okay? So we're going to look at a table where we have the guidelines depending on the condition or the application. We have a range that you could have your factor of safety in. But one thing that I can also say is that when you use factor of safety for your design, in effect, you are over designing the member, in the sense that you design the member so that it can withstand stresses higher than what is designed for. And that is where the factor of safety will assist in that regard. So we don't want the factor of safety to be too high, okay? If it is too high, it means that we have over-designed the member. If you are over-designing, means that you're going to use so much material for it, which may increase the cost of it. Or maybe the weight of it may also be very high. In certain situations, we don't want very high weight, like they're using the aerospace industry. An aircraft fly in the air, we want the weight to be as small as possible. So where there is no need for higher value of factor of safety, we need to ensure that we decrease it. And where we are very uncertain about the situation, we may increase the factor of safety. So we have this table showing the ranges of factor of safety. So let's see the first in the first row we have the factor of safety and the application. Then factor of safety of 1.25 to 1.5. And note here that the factor of safety is greater than 1 from the beginning, okay? If it's greater than 1, it means that if it is 1.5, it means that please mute your microphone.
So looking, what's the what the field trip no so Friday?
Hello, please mute your microphone. Okay. So from 1.25 to 1.5, and these are for exceptionally reliable materials used under controlled condition and subjected to loads and stresses that can be determined with certainty. Used invariably where low weight or lightweight design is a particular important consideration, okay? So what we have lightweight designs like the aerospace industry and the other things where you want to ensure that the weight of materials are as light as possible, then we have a factor of safety in this range. Shown in detail, the material properties, operation conditions, loads, and resultant stresses and strains. Technical requirements like material test certificates, proof loading, regular inspection, and maintenance. So in such cases, if you have this factor of safety within this range, though it's low, but it's okay. And then 1.5 to 2 for material conditions, well-known material for normal material conditions. So well-known materials under reasonably constant service conditions subjected to loads and stress that can be determined readily. So when we can determine the loads and stress readily, then this will be the factor of safety range. Then the known, that is known that you know the material properties and the constant environmental conditions, loads and stresses determined using qualified design procedures, technical requirement like proof of tests, regular inspection, and maintenance. So if all these things are to be done or you have knowledge of them, then the range from 1.5 to 2 is acceptable. Then from 2.0 to 2.5, materials are obtained from reputable suppliers. Designs are for operations in normal environments. Loads and stresses that can be determined using checked calculations. In such cases, from 2.0 to 2.5 is acceptable. Then we also have the range from 2.5 to 3.0 for less tried materials or for brittle materials under average conditions of environment. Under average conditions of environment, load, and stress. Then from 3.0 to 4.0 for untried materials used under average conditions of environment, load, and stress. Also, against ultimate failure of brittle materials. And then we also have 3.0 to 4.0, where which could be should also be for should be used with better known materials that are to be used in a certain environment or subject to uncertain stresses. So the materials are known, but if the operating conditions are not certain, we could use 3.0 to 4.0. Then from 4.0 to 6.0, for specific service conditions, example, rough service conditions or unusual conditions, then this range would also be used. Okay. So let's continue. So we look at design equation. The design stress, sigma D, determines the design stress, sigma D, determined at the discretion of the designer or the engineer using specific guidelines, is the limiting stress which should not be exceeded in the processing of a machine member. Okay, and this is expressed in the form of the equation. The stress should be less or equal to the design stress. That is, the stress in the machine member. The machine member is in operation. That stress in it should be less than or equal to the design stress. We don't want it to go above the design stress. Then the calculated stress should be equal to or less than the design stress. And in this form, the design equation provides an important basis for determining the size of the machine member. Okay, so we are going to end here. Then, God willing, I mentioned to you that next week you'll be having your second quiz. And how many quizzes are we writing? Is it 2 or 3? Hello?
2.
2. Okay.
Yes, sir.
So we'll have the last one next week. I think should be on Thursday, God willing. But on Monday, we'll have our last class to wind up everything. Okay. So on Monday, we'll have our last class to wind up everything. Thank you very much for coming, and see you later. God bless you.